Hello and welcome to a new video in a course on linear algebra. In the previous videos, we defined linear transformations and the kernel and the images of linear transformations, and we've given some examples and properties of these. Namely, we proved that the kernel and the image of a linear transformation are actually subspaces of the domain and the codomain respectively. Now, and I remind you, the reason we're studying linear transformations is that we're interested in vector spaces, and usually you'll see, if you take more math courses, you'll see that usually when you want to study a mathematical structure, studying maps between mathematical structures usually is very helpful. And we've defined what a linear transformation is, and in this video we'll be studying two important classifications of linear transformations. So just as a reminder, a linear transformation is this map between two vector spaces V and W that satisfy the property that T of V1 plus R V2 is equal to T of V1 plus or T of V2. So it's a map that respects the addition and scalar multiplication of the vector spaces, and this is happening for every V1, V2 in V in the domain and R real number. Now the first definition we're gonna make in this video is the definition of injective linear transformations. So what are these? So the linear transformation, it's a map between two vector spaces between V and W, say. So injective linear transformations have the property that if you have 2 points in the domain and these points are not the same, if these are different, then they cannot map to the same. So they cannot map to the same point. So if they map to the same point, they gotta be the same. So if they're different, they cannot map to the same point. So this is what I'm trying to say. So let me just state it in mathematical notation. A linear transformation is said to be injective if whenever T of U is equal to T of V, we have U equals to V. So if you look at the counter positive of this statement, you see that if U is not equal to V, then it must be that T of U is not equal to T of V, right? So this is what we have. So if the images agree if the images of two vectors agree, then it's gotta be the case that the inputs were the same. So this is the definition of what an injective linear transformation is. So let me just give you an example here just to make the definition clearer. So we know that Euclidean spaces are vector spaces, so let's consider the linear transformation between these, between R2 and R3, that takes xy, takes the vector from R2, so this is in R2, takes this vector to xy0. Right? So this is the linear transformation we're talking about, and I'll leave it to you as an exercise. It's a fairly easy exercise to show that this T is actually a linear transformation. Now we wanna prove that this is injective. So what we're gonna do is that let me just write things here. So if we take T of x1, x2, or let's take T of x1, y1, and we're supposing that these are the same, so the x2, y2. We want to prove that x1, y1 is equal to x2, y2. So if the image of two vectors, if the images of two vectors agree, then it must be that these vectors are the same. It must be that the input is the same. How do we show this? Well, we use the definition of T. This is the same as x1, y1, 0 equals to x2, y2, 0 by definition. And since since tuples agree component-wise, this forces x1 to be equal to x2 and y1 to be equal to y2, and thus this forces x1, y1 to be equal to x2, y2, and this is the proof of injectivity. Look at the definition and look at what we proved, then this proves that T is injective. Now, quite often, there's a yet easier way of proving injectivity, which is that we prove that the only vector that goes to 0 is 0 itself, right? However, for that we need to prove something. So let me just prove a property about injective linear transformation that is it's injective if and only if the kernel of that map is 0. In other words, if you have this map T, this linear transformation T from V to W, then it's injective. Like, we know that it's injective from the above definition if and only if any two non-equal vector gotta map to two non-equal images. So it gotta be the case that if they map to the same vector, if they map to the same image, then they gotta be the same input, right? So this is what injective means. And here we're saying that there's an equivalent way of defining this, which is that if you look at this T, right? So we want to prove that the kernel of this map, and I remind you, the kernel, it's the set of all vectors. So the kernel of T, it's the set of all V's in the domain such that T of V is 0, right? So this is the kernel. And we're claiming that the linear transformation is injective if and only if the kernel is equal just to 0. In other words, the only vector in the domain that goes to 0 by T is the 0 vector, right? So this is what we want to prove. So let us prove this, and before that, let me just tell you why this is important. It's quite often easier when you want to prove that a linear transformation is injective. It's often easier to prove that the kernel is 0. The kernel is just the 0 set, right? Like, you only prove that if T of V is 0, then V gotta be 0, and that's it, right? So it's kind of easier than showing this often. So let us prove this equivalence here. So here's a proof. So let's see what this proof is. So let us prove this direction first of all. So suppose T is injective. And what that means is that this means that this definition is satisfied. It means if T of U is equal to T of V, then it must be that U is equal to V. This is the definition of injectivity, right? So we know T of U equals T of V implies U equals V for every UV in the domain, right? So this is what we have. So what we want to show is that the kernel of T is equal to the 0 set. Now we do know that this direction is clear. So we know that 0 is a subset, the singleton 0 is a subset of the kernel. And why is that? Well, this is the case because we know that T of 0 is equal to 0 whenever T is a linear transformation. So if T is a linear transformation, we know that T of 0 is equal to 0. This was proved in the previous video. And thus this set is contained in the kernel, right? Because 0 is thus in the kernel. So the next question is, why is this containment true? Why is it that the kernel is contained in 0 if we have this property? Well, so to do that, we're gonna start with a vector V in the kernel, and we're gonna prove that it gotta be in this set, i.e. it gotta be 0, and thus we prove this containment, right? So let V be in the kernel, then T of V is equal to 0. I hope you agree with me, because this is the definition of the kernel. But 0 is itself equal to T of 0. This is this is something that we proved in the previous video. And thus, if we use the property star, we have T of a vector is equal to T of another vector. This implies that V is equal, like the input is equal to the input, is equal to 0. And this is what we wanted to show, right? This implies that the kernel of T is contained in this zero singleton. And this is the proof of the forward direction. So let us now prove the backwards direction. We want to assume that the kernel is the zero singleton, and we want to prove that the linear transformation is injective. So let us prove this now. So suppose that the kernel of t is equal to the zero singleton, and we want to show that if t of u is equal to t of v, then u is equal to v. This is the definition of injectivity for every u, v, and v. So this is what we want. So to do that, let u and v be in v, and suppose that t of u is equal to t of v, and what we want to show is that we want to show that u is equal to v to prove that the map is injective. Okay, so from this we want to use something from what we have, right? So it would be better to find a vector in the kernel and try to impose the fact that if a vector is in the kernel, it's gotta be zero. So this is what we're gonna try to impose, right? So if we can prove that u minus v is equal to 0, we'll be done. Because then u is equal to v, and this is what we want, right? So we want to prove that u minus v is 0, and the only property that we have is this thing. We have the property that if a vector is in the kernel, then it gotta be 0. So let us check if this vector is in the kernel. This vector here is in the kernel, because if it is in the kernel, then it gotta be 0, and we'll be done. So t of u minus v, let's check if this is 0, and thus it's in the kernel. It's equal to t of u minus t of v. So because t is a linear transformation. But wait a sec, we know that t of u is equal to t of v, and thus this thing is actually 0. And this implies that u minus v is in the kernel of t, which is equal to the 0 singleton from here. And thus this implies that u minus v gotta be 0, right? So this implies that u is v, and this implies that t is injective, as desired. So in this way we would have proven this backwards direction. And thus from now on you have two definitions of what an injective linear transformation is. You either use this property stored, or you use the fact that the kernel gotta be the 0 singleton. Okay? In other words, the only vector that maps to 0 is 0. So this is all I wanted to say about injectivity for now, and let us discuss what's so-called surjective linear transformations. So again, this is what we have, right? So the image, we agreed that the image is a subspace of the codomain. We agreed that the image is actually a subset of the codomain. So this is the image of T. Now, what this property or what this definition says is that T is said to be surjective if the image is equal to the codomain itself, right? It means that every element in the codomain gets hit by T, right? So, in other words, the vector space V gets mapped to omega itself. So this whole thing is the image. This whole thing is the image, because the image is equal to T. So this is what it takes for a linear transformation to be surjective. And I remind you, one important thing about the image is that how would you prove a vector? Reminder: how to prove a vector V is in the image of T. You need to find a vector v prime in V such that t of v prime is equal to v. If you can find such a vector, then you get that v is in the image, because recall the image is the set of all vectors t of v as v ranges over the domain v, right? So this is what we have. So let's take a quick example here to see or to understand the definition. So let's take the linear transformation between the vector space R2 and itself, and we're gonna take the tuple xy to the tuple x plus y and y. So this is how we're defining the linear transformation T. And the question is, what's the image of T, and is it equal to R2? In other words, is the map surjective, right? So the first step is to find the image, and then to ask yourself, is it equal to R2 or not? So the solution is over here, but let us just rewrite things to understand what's going on. So let's find the image of T. The image of T, it's the set of all vectors T of V as V runs over R2. Now what does a vector take? What's the form of a vector in R2? It's xy, right? So let's say it's the set of all vectors T of xy such that xy ranges over R2. Now this is equal the set of all vectors from here x plus y, y as xy ranges over R2. So this is what the image is. Now the question is this equal to R2? Well, we know that the image is always a subset of the codomain. So the only question here is whether or not this containment is true. In other words, the only question is whether there is an element in R2 that is not contained here, right? If there is an element in R2 that's not contained here, then this equality cannot be true. However, if every element in R2 is contained here, then the image is equal to R2 and the map is thus surjective. So let us see why this is. So let us see why it's surjective, because I actually claim it's surjective. So maybe I should show you here. So start with any vector in R2. So we start with any, because we want to prove this containment, we start with a vector here and we show that it's here, right? So start with any vector in R2, right? So we want to find another vector, because remember, this is how we show a vector is in the image, right? We want to find a vector in R2 in the domain such that T of xy is equal to AB, right? But remember, this is how T is defined. T takes a vector xy, it adds the first component to the second, and it leaves the second component the same. So we know for sure that y should be b, right? If we can find such an xy, then y should be b, because T leaves the second component the same, and we want the second component to be b. Now, can we choose the first component in such a way that when we add the first component to the second component, we get a? Well, sure we can. We can take a minus b, because if y is b, then a minus b plus b is a, and that's it. Like you get this tuple, which is a minus b b, such that when you take T of that, you get AB, and this proves that AB is actually in the image. So this is in the image of T, and this proves this containment, and thus this proves that the map T is surjective as desired. Alright, so just a small note here. Some people refer to injectivity, they call it one-to-one map, and they refer to surjectivity and call it onto. Yeah, it's just a convention, but I think injectivity and surjectivity are more common. And this is all I needed to discuss in this video.